Swayam Prabha. Digital India. Educated India.
So, welcome to the lecture today. What we have seen so far is basically solving linear algebraic equations and linear ordinary differential equations, okay. And we were working in what we call finite dimensional vector spaces, because the number of coordinates in each of the vectors were finite, okay, they were not infinite. So, we are now going to shift and start talking about using whatever we have developed for finite dimensional vector spaces to infinite dimensional vector spaces. So, when I mean infinite dimensional vector spaces, basically we will talk about partial differential equations. So, basically how can I extend whatever we have seen so far to the context of partial differential equations, and I will explain to you why I mean it is going to be an infinite dimensional space, okay. So, okay, rather than keep the suspense for too long, I will tell you why it is an infinite dimensional space. When you are talking about solving a partial differential equation, you are looking at finding some function of x or y or t, okay. So, and this function, when solving a PDE, for example, the solution is a function of x or y or t, whatever it is, and this function is defined over some interval, okay. I will give we will talk about this with an example. This function is defined over an interval. It could be 0 to 1, a to b, whatever it is, because that is the domain over which your equation is valid, your system is extending. And in this interval, so basically you have a function, maybe u or t of x or u of x. So, u of x is defined for x belonging to 0 to 1, and in this interval you have an infinity of points. So, I mean that is a very simple way for you to think of this as belonging to an infinite dimensional system. The function u of x is defined over an infinity of points, and therefore, you know, one likes to think of this in terms of being in an infinite dimensional space, okay. And since as there are an infinity of points, we think of this as an infinite dimensional space, okay. So, I mean just to whereas when we were solving problems earlier, you had 2 dimensional vector, 3 dimensional vector, depending on the particular problem that you were dealing with, okay. So, now coming to partial differential equations, certain things you already know. We are going to focus on second order, What is the order of a PDE? You all know this is the highest order derivative which is present in the equation, okay. The highest order derivative present in the equation, okay. And as far as degree is concerned, degree is the power to which this highest order derivative is raised. So, degree is the power to which this highest order derivative is raised. And these are things you know. What we want to do is we are going to focus mainly on second order equations, because in most of the processes that we will encounter, these are going to be second order because of the physics of the problem, okay. So, our focus why second order equation? Because yep, why second order? Because if you look at heat conduction, heat equation, you will have rho Cp dt by dt equals k d square T by dx squared. That is the second order equation. Whenever you have something like thermal conduction, it is like a diffusive in mass transfer you have diffusion, that is also going to give you a second order equation. In heat transfer you have thermal conduction which gives you second order. In momentum you have the viscous term which is second order. So, all of these are second order, okay. So, I mean we just going to look at second order equation. Similarly, you have d square C by dx squared, or you have mu del squared V in mass and momentum transfer, okay. So, this is just to tell you that we are just going to look at only second order equations so far. So, whenever you have a differential equation, I will begin with an example. Now, I am going to talk about let us say the energy equation. So, we are talking about temperature, okay, and I am going to say this equation is of this form. So, I am now going to use the word dimension to talk about spatial dimension. So, earlier when I was talking about dimension of vector space, I was talking about number of coordinates, okay. 3 dimensional means 3 coordinates, n dimensional means vector has n coordinates. That did not have any concept of spatial dimension, but now when I am talking about dimension here, I am talking about spatial dimension. So, this is I will call it a 2 dimensional system because it is extending in both x and y direction, okay. This is 2D system extending in x and y directions. If it is only extending in y direction, then I will call it 1D, x, y and z I will call it 3 dimensional, okay. So, it is just I am using the same English word, but physically it means different now. So, this equation basically represents, physically it would represent the steady state temperature in, because I am talking about x and y, we are looking at a system in Cartesian coordinates. Okay. So, this the solution to this equation yields steady state temperature in rectangular domain. Okay. And let us say, for the sake of concreteness, that this rectangular domain extends from x a 0 less than equal to y less than equal to b. Okay. So, I have 0 x equals 0 here, x equals a, y equals 0 and y equals b. Maybe I should not have these extra things sticking out. Okay. So, x is going from 0 to a, y is going from 0 to b. Whatever is on the boundary, I am going to call it either the surface or the boundary, and whatever is inside, I call it domain. So, this is the domain and this is the boundary. Okay. In order to solve this equation, I need to specify boundary conditions, okay, in x and y. So, it could be some temperature, since we are talking about temperature and energy equation, it could be either I am heating it at a particular rate, maintaining temperature here, or insulating. So, physically there is a particular system, okay, and this what is happening physically, I need to translate it to equations. Okay. So, on the boundary we specify boundary conditions from the physics of the situation. So, my point is, inside the domain, inside here, that differential equation is valid. Everywhere inside. Okay. On the boundary conditions are valid. So, one particular example of a boundary condition could be temperature. Let us say this boundary. What is this boundary? X equal to 0, y is changing, right. Temperature at x equal to 0, let us say, is equal to f of y. Along this line, y is changing, x is fixed. So, temperature is going to be a function only of y at x equal to 0. So, I am specifying some temperature profile, it could be constant, okay, and let us say temperature at y equals b is equal to g of x. Y equal to b is the top surface. So, here I am saying temperature is equal to g of x, here I am saying temperature is equal to f of y along this wall. Okay. So, what you understand is that this point here, x equal to 0, y equal to b, is common to both the walls. Okay. What is the temperature at x equal to 0, y equals b? If I go along this wall, it is going to be given by f of b. If I come along this wall, it is going to be given by g of 0. Okay. Let me write it like this, let me not put it equal here. So, you are looking at the same point, okay, but if you come along one value, one wall, one boundary, you are getting f of b, another thing you are getting g of 0. So, basically you would like f of b to be equal to g of 0, only then, I mean, it is consistent, okay, the problem is well posed, but otherwise it is ill posed, okay. So, basically a well posed problem requires f of b to be equal to g of 0, because if you measure the temperature along this direction and this direction, same point, okay. So, then you will get a solution when you solve, you will get a solution which is smooth, continuous and all that. But supposing if f of b is not equal to g of 0, then I have an ill posed problem. So, if you want to solve this problem numerically some way, you will find that near that corner or edge, whatever you want to call that point, you will have something non smooth, okay. Some numerical it will not be smooth, at other points it will be well behaved, okay. So, near, if it is ill posed, near that corner 0 comma b, what is it 0 comma b, yeah, 0 comma b, the solution will be maybe not very smooth. If ill posed, solution near 0 comma b will not be smooth, okay. So, ideally you want things to be well posed. Now, I need to specify, so whenever you are talking about solving a differential equation, you need to specify things on the boundary, because this is easy for you to see. Here, for example, temperature is f of x and maybe I am going to heat this guy here. So, dt by dy to q, and let us say I will put dt by dx equal to 0. What have I done? I am specifying conditions at all the boundaries, okay. What is dt by dx equal to 0? Physically mean I am insulating it, there is no heat flux. What is dt by dy minus dt by dy equal to q minus dt by dy, because there is the flux in the positive y direction is q, and let us say q is positive, then that is the rate at which I am heating, heat is entering the surface, okay, into the domain. So, basically here this corresponds to minus dt by dy equal to q at y equal to 0 implies constant heat flux, okay, and this is at y equal to 0, and dt by dx equal to 0 at x equal to a implies adiabatic, okay. So, my point is these conditions, these boundary conditions that you normally use for solving a problem come from physical things, physically what you are doing in the system. If you are supplying heat, then I will use this kind of a condition. If I am insulating, I will use this. If this heat transfer, if I am maintaining the temperature, okay, we will discuss this, we will get this kind of a boundary condition. Now, because the equation is second order in x and y, I need two boundary conditions, two in x direction, two in y direction, and that is what we have here. Okay. I have one equation for x equal to one boundary condition x equal to 0, one boundary condition x equal to a, second order in x, second order in y, one boundary condition here, one boundary condition here. Okay. So, basically if I have second order in y, I need to have two conditions in y, second order in x, I need to have two conditions in x, and then when I am solving it, I will get some arbitrary constants of integration, which I can calculate by using the boundary conditions. Okay. So, because equations are second order, we need two boundary conditions in x and y direction each, okay, and that is what you have. So, normally what happens is you need to specify, basically what we have done is we have taken the boundary, in this case is very clear for you to see that x equal to 0, x equal to a, y equal to 0, y equal to b. But what have we done? We have actually specified conditions all along the boundary. Okay. So, that is the reason it is called boundary conditions. So, these boundary conditions are all along the boundary. Okay. So, what I am saying is we can extend this to an arbitrary shape. It does not have to be a rectangle. Okay. So, let me draw an arbitrary shape here, that is as arbitrary as I can get. Okay. And inside here again we will keep it 2 dimensional. I will say d square t by dx square equal to 0 plus d square t by dy square equal to 0. That is valid inside, but I need to specify conditions everywhere on the boundary. Okay. I mean, it could be f of x, it could be flux, it could be the derivative, it could be something. Okay. So, I can specify. So, let us say this is the boundary a, b, c, d, e. Okay. So, I want to find out again what the temperature profile is inside this arbitrary shaped body. So, I need to specify boundary conditions everywhere on the boundary. So, that is the point I am trying to make. The earlier problem, it was easy for you to see second order, I need two conditions in x and y, okay, and I gave you a nice beautiful shape rectangle. But if I want to generalize it, basically what I am trying to do is I am specifying conditions everywhere on the boundary, some either derivative or temperature, and same thing I have to do here. Okay. Even if it is an arbitrary shape, I will say on the surface A, B, C, let us say temperature is equal to something, is some value is equal to let us say 100, and on the surface A, E, D, C, let us say I have no flux. Whatever it is not correct. Yeah, gradient of heat. So, what we are talking about is the gradient in the direction which is normal to the surface. So, this is actually not correct, because this could be x direction, this could be y direction. If if I say I am insulating this, I am not talking about the flux in the x direction, I am talking about the flux in the outward normal direction. Okay. So, basically this is not correct. What I would like to do is write this as n dot del T equal to 0. In the earlier problem, n was either x or y. Okay. So, I could write it as dt by dx and dt by dy, but in this problem the outward normal direction is changing from point to point. Here the normal is in this direction, here it is in this direction. So, at every point when I am saying insulated or when I am talking about the flux, I am talking about the outward normal derivative, and this is what you have to use. Okay. So, the only way people can learn is when they make a mistake, right. So, I am also learning by making a mistake. dt by dx is wrong, you use n dot del T. Okay. So, again point is I am specifying things on the boundary. So, now I can solve this problem because conditions are specified everywhere on the boundary and the differential equation is specified everywhere inside. I can look for a solution, but if I do not specify conditions here or here and say solve, I can't solve. Okay. So, people when you look at articles, research articles, there are people use different conventions. So, basically I am doing this so that when you read some article you will understand what they are trying to say. So, they might say, so del square T equal to 0 is valid in the domain, and people may like to use V or omega for domain. Basically that is a symbol for the domain. In our earlier problem, V was 0 to A, x going from 0 to A, y going from 0 to B. I am just representing that as V or omega. Okay. This is 0 less than x less than A, 0 less than y less than B in the earlier problem. So, rather than write every time, I will just say V and you understand it is there. Similarly, boundary, okay, people will use the notation S for surface or dou omega for boundary. Okay. Similarly, for boundary, people use S or dou omega. That omega is capital omega. Okay. I mean that is just notation. So, you suddenly reading something and you see some dou omega showing up, then you have to understand that that is the boundary. S is boundary, V is domain. Depending on different people, they use different notations. Okay. Because every time you can't write 0 less than x less than A, 0 less than y less than B, things like that. Okay. So, whenever you are solving a problem, point is domain has the differential equation and boundary has boundary conditions, and it was easy for you to see second order equation, two boundary conditions, but this is an arbitrary domain. You just have extended from rectangular domain to arbitrary. Let me look at an unsteady problem where you have dt by dt So, physically what we are looking at is how does the temperature evolve in time and in space, okay, and time will extend from 0 to infinity and x may be whatever finite, x could also be infinity, but we can right now we will keep x finite. So, let us say 0 is less than x less than 1 and t is greater than 0. So, I am going to look at time as one of my coordinates also. I can see just a variable. So, it does not have to be only spatial dimension, it can time can also be looked upon as a dimension. Okay. So, here in space time domain, let us say this is x 0 to 1 and this is t going to infinity, going off to infinity here. It is not bounded on the top, okay. And in order to solve this equation, I need to give one condition, one initial condition, which is at t equal to 0, this t is increasing, this t equal to 0 and t increases vertically, x is changing horizontally, okay. So, temperature at t equal to 0 is, let us say, T naught of x, because time is fixed. Initially I can have some temperature in the slab which is varying from in the x direction, and then I need boundary conditions at this is x equal to 0, this is x equal to 1, temperature at x equal to 0 is, let us say, 30 degrees and temperature at x equal to 1 is 100, okay. Physically, what does this problem correspond to? I have a slab which has some temperature T naught of x, T naught for time t equal to 0, okay. T naught of x is the temperature. Suddenly I am putting it in a liquid, let us say, one side is at 30 degrees, another side is 100 degrees. So, there is going to be some heat transfer. Now, when does this kind of a condition be physically relevant? When if the temperature of this liquid or air whatever is 30 here and there is no heat transfer resistance. So, the temperature of the liquid outside, this is solid, okay. I am immersing the solid in a liquid, on one side of the liquid is at 30 degrees. So, there is a liquid at 30 degrees and this is at 100 degrees. If there is no heat transfer resistance in the liquid, then the temperature the wall is going to see is 30 degrees, the temperature the wall is going to see on the other side is 100 degrees. So, physically it means your liquid is getting very well mixed. So, there is no heat transfer resistance, okay. And we are asking how does the temperature in the slab change with time and x, okay. Initially it is at this temperature, how does the temperature change as a function of x and t. So, physically we have a region with temperature equal to T naught of x, okay, and on the left we expose to a well stirred liquid. So, well stirred means negligible heat transfer resistance. So, if liquid on the left is at 30, then wall will be at 30. Physically that is what it is, okay. Similarly, on the right hand side, if the liquid on the right is at 100 and the heat transfer resistance is negligible, I can say temperature is 100. So, that is the physical meaning, okay. Similarly, on the right, if liquid is at 100, what is it, 100, right, and well stirred, temperature at the wall will be equal to 100. But if the liquid is not well stirred, then you have to modify the boundary condition. You will have to use Newton's law of cooling, we will see that. Okay. The point is, I mean, everything that you are doing has a physical relevance. I mean, you are doing mathematics, but it is not just mathematics without any life, without any John. Okay, there is life in it, and you have to understand the life. Only then you can appreciate the results. Otherwise, you are just solving a problem, you are getting some results, you won't be able to appreciate the what you have done. So, you have to keep in mind the physical interpretation of whatever is being done. Okay. Again, I want to make sure that T naught of 0 must be equal to 30, T naught of 1 will be equal to 100 for a well posed problem. Okay. Because only then, otherwise it is a, if it is not at 30, when imposing at 30, suddenly there is going to be a step change. So, you do not want step changes, you want smooth profiles. Okay. I mean, yeah. So, this is the same as a well posed problem that I spoke about earlier. Okay. And both have to be satisfied for well posed. Even if one is satisfied, the other is not satisfied, it is ill posed. What I want to do is talk about of second order PDEs. So, now you can categorize these second order PDEs as being elliptic or parabolic or hyperbolic. Okay. Or and how do you decide which category this guy, the differential equation belongs to? In fact, what we are going to do is mainly focus on elliptic and parabolic. Most of the time that is what we see. Hyperbolic occurs also in some cases, but we will focus only on these two, but the methods are all similar. So, we can write a second order PDE can be written as to 3 what have I done? If I have a second order partial differential equation, I am writing all the second order terms on the left, all the first order terms and the terms without any derivative I am writing it on the right hand side. And since we are going to look at physical problems, the maximum can have 3 directions x, y, z, okay, in Cartesian coordinates. So, this xi, x1 is x, x2 is y, x3 is z, okay. Rather than write xy, because then I can't do the summation sign, I have to write 9 terms. because I will have the second order, the mixed derivative, and all those terms are going to show up. I will write each and every term. So, this helps me give a compact representation of my second order term. Okay. So, and this is basically the one which is associated with the thermal conductivity or the diffusion coefficient. So, basically if you have cylindrical coordinates, x1 will be r, it could be r, x2 could be theta, x3 could be z. This is in cylindrical coordinates, this is in Cartesian coordinates depending on the problem. Okay. This is cylindrical. Now, we can have this aij as a function of x also, but just keep that in mind, but let us right now forget about that and just treat this. So, what have I done? Given a differential equation which is second order, all the second order terms, the mixed derivative, the non mixed derivative, all I am keeping on the left, all the first order, all the lower derivatives I am keeping on the right. Okay. I am going to focus only on the left hand side, and I am going to write this matrix. I am going to look at this matrix A. So, we look at the matrix A which has elements A11, A12, A13, I look at these matrix elements. What are these? These are the coefficients which are sitting here. Okay. So, for example, if I have d square t by dx squared, I will have, this is implies A11 is 1, because 1 is multiplying this, and x is my x1 term, my first coordinate. Okay. If I have d square t by dx dy, let us say 4, then what is this? A 1 2 is 4. Okay. What I want to do is do the classification in terms of the eigenvalues of this matrix. Okay. And I want to ensure that these eigenvalues are real, which means my matrix has to be real symmetric. Okay. So, now you say if you have a term d square t by dy dx is missing, suppose it is missing, then A21 is 0, because there is no term. So, now I do not have A12 equal to A21. So, what do I do? I recognize that these two are equal anyway, d square t by dx dy is equal to d square t by dy dx. So, I can write this as 2 times d square t by dx dy plus 2 times d square t by dy dx. Okay. Basically, what I am trying to tell you is I can write 4 times d square t by dx dy as 2 times d square t by dx dy plus 2 times d square t by dy dx, because d square t by dy dx is equal to d square t by dy dx. Okay. So, now I have A12 equal to A21. Okay. So, this is because the point is you can always use this, exploit this property that the order of the derivative, the differentiation can be interchanged, and you can ensure that you have a real symmetric matrix. Okay. So, if you remember this, we can hence always get a real symmetric matrix using this. Okay. So, basically given any second order partial differential equation, I can look at these coefficients and use this symmetry of the mixed derivative and get a real symmetric matrix like I did just now. Okay. So, now what is the classification? If all lambdas are positive or all are negative, then equation is elliptic. If one lambda equals 0, then it is parabolic. If some are positive, some are negative, it is hyperbolic. Okay. Yeah. So, let us stop here. I will tell you some physical meaning about when these equations arise, and then we will look at how to solve these problems. Thank you.